We've got the system working. Come on, that, otherwise I can see I'm going to fall down a hole there. Another delay. Yeah. Okay. Is that on the? Okay. Right. Right. I think at last we are operational. A little bit of general background before I get underway. As some of you, maybe many of you know, my background is in what I would call classical fluid mechanics, applied mathematics. And for very many years, my interest in waves and nonlinear waves did tempt me in the direction of oceanography, but I have to admit that I ran away from such studies. I felt that they were just too involved, too complicated, and that conventional applied mathematics was not likely to be that useful or even produce some reasonable results. But 3 or 4 years ago, and again some of you will know I've worked with Adrian for quite a number of years now, he suggested that I have a look at problems in oceanography, and I have to admit that I was initially very sceptical indeed. But he had done his background reading, and he pointed out to me that there were quite a number of areas where rather limited areas in the oceans, maybe standing well back and very global pictures of the oceans, where some sort of classical fluid mechanics might play a role. And indeed that has turned out to be the case, and I think we have managed to cover a reasonable number of quite interesting problems. What I want to do today is to give you an outline of those ideas. Now this will not be explicitly nonlinear waves. We will say a little bit about waves in one of the earlier discussions. It certainly will involve nonlinear fluid mechanics. Also, certainly, much of what I'm going to say will provide a background to material that can be extended into wave and nonlinear wave propagation. I guess also in part, I'm going to be covering what I might call a general philosophy of my ideas of fluid mechanics and how they apply. I am going to be talking about applied mathematics. I'm not going to be talking about pure mathematics, so there will not be the sort of rigor that some of you are looking for or hope to see. That cannot be done in this sort of work. I'm not going to do physical modelling either. I have to admit that's something I feel a bit uneasy about. I'm certainly not going to do any numerical simulations, nor do I have any experimental apparatus with me. This is going to be conventional applied mathematics. So I have indicated here in outline what we're going to be having a look at. I'm going to assume, and this is the first talk, so I thought it might be reasonable to have some sort of rather general introduction to the sort of problems that we're going to be talking about. So I will say something about the approach. I've almost covered that already. I will then show you some relevant oceanic flows, the sort of things that it does look as though we can get a handle on and make some headway with. Obviously, I'll then formulate the problem, the governing equations to the boundary conditions, and one of the standard models that's used in oceanography, I would just mention in passing, the so-called tangent plane approximation. More importantly, I will then run through, perhaps that's putting it a little too strongly, but I am not going to cover a lot of fine detail here. That will not be possible. I really want to show you what a conventional applied mathematical approach can do in some areas. So I will touch on a very routine problems, linear waves, a very messy problem as well. I do hope that as I work my way down this list, ending up with modelling gyres, I will be able to show you things that are a little bit more interesting, a little bit more exciting, mathematically certainly more interesting, with appropriate applications. So let's see if we can get underway. Excuse me, one thing I have found as I've aged is that I do need water. It is water, by the way. So, motion of the oceans. I've put some things down here. There are going to be at least some in the audience who are probably more expert at what's really going on than I am, and they could probably add to this list. So we've clearly got wind-driven surface waves. We've got underwater currents, upwelling, downwelling. We've got thermal density and salinity stratification, and that would give rise to thermoclines and pycnoclines. And there's more. And on top of all that, there will be changes on different time scales. There will be seasonal and climatic changes, tides, turbulence, and I'm quite sure you can add others. It is one of the reasons why I didn't get myself involved in this years ago, was because of the total complexity of these sort of problems. There's a lot going on. Right, well, I suppose in a sense what has prompted it in my reading of the more modern works on oceanography is that over the last 40, maybe 50 years, there has been a vast amount of really very good data that's been collected. And it really is, at least in part, a matter of trying to understand and interpret that data that has driven a lot of the modern thinking. I hope I'm not upsetting anybody by saying that typically my reading of what happens in this area is that you either construct a physical model, I call it an ad hoc model, you just put together the things that are physically relevant, you think, for the particular scenario that you're interested in, or you carry out, and there's some extremely good numerical simulations of flows of this type. I propose a different approach. The application of the ideas and techniques, and I hope that if you're not already familiar with the way I do these problems, I'll be able to show you a little of my thinking and the way in which I approach fluid mechanical problems using what I would regard as a very conventional applied mathematical approach. So, there will be quite a number in the audience who are not familiar with oceanography in general, but almost certainly not with the specific types of flow that I'm going to describe. So let me give you one, two, in fact I think I'm going to give you three. So here's the first one. This is the flow near the equator in the Pacific. The white line there is the equator, running from west to east. In a relatively narrow band close to the equator, we have a really quite well-structured but complicated flow. We have a thermocline, which is altered by El Nino effects, for example. Warmer water above, colder water below, and this thermocline generally rises from west to east. There is, near the surface, essentially wind-driven, you have a flow away from and back in the westward direction near the surface. A bit further down, you have the undercurrent, this is so-called equatorial undercurrent, a much faster stream which is moving from west to east. So you have, in fluid mechanical terms, albeit rather isolated in terms of the oceans, a relatively well-structured problem. And analysing, for example, waves propagating both on the surface and on the thermocline with this background structure is certainly something that we can examine. I'll obviously come back to it shortly. Completely different sort of flow, the Antarctic circumpolar current. There's a sketch of it. This is the only current that completely encircles the globe, and you can see roughly where it travels in that sketch. Its total length is round about 23,000 kilometres. Its maximum width is about 2,000, at narrowest a few hundred kilometres. You can see there are wider sections and narrower sections. The overall average speed does vary from place to place as you move around, but across a cross section it could vary between about 4 and 25 centimetres per second. What's really quite intriguing is that actually it's made up of a small number, maybe half a dozen, of high-speed jets. That essentially comes about because there's, that comes about because there's a lot of mountains, there are mountain ranges below the ocean surface which guides the flow and channels it, giving rise to essentially narrower, 40-50 kilometres wide, high-speed jets. The reference here then is to the overall average flow speed and therefore mass flow rate that you can compute. So a reasonable way of tackling such a problem would be to ask, well, can we get anywhere near an analysis of a circular flow, for example, that goes around the polar axis? I'll come back to that one shortly. Gyres. Well, gyres are really very significant in terms of ocean motion. There are 5 major ones. I've indicated there in the sketch. There are many other smaller ones. They are very stable and they have very predictable properties. The main factors that control a gyre, the main driver indeed, is the global wind pattern. This drives the gyre in terms of the local prevailing wind directions. There's the rotation of the Earth, of course, and naturally they are constrained, and they're going to be constrained because of the existence of the land masses, as you would expect, and associated with that the bottom topography. There are 3 problems. The first one is a relatively straightforward wave type problem. The second one could be, one would hope, modelled, albeit as a circular flow around the pole. And then can we get, sitting on a rotating spherical surface, can we get flow patterns that look something like this? And we can touch on 1 or 2 other aspects as we work our way through. So I'm going to pause there for a minute. I've got started. I'm beginning to warm up. Please don't hesitate to ask questions as I go through. If I kind of give you a quick and simple answer at the relevant point, I will do so. Clearly, I'm not going to give a lengthy answer. We can leave those to the end if that becomes necessary. But please stop me at any stage if you want to ask me something. Right, well, let's formulate the problem. For this talk, I'm going to take the simplest possible formulation that's available to us. So, I'm going to take an inviscid fluid. We're currently working on the application of Navier-Stokes to some problems. But in this demonstration, I'm going to talk about an inviscid flow, but it will be rotational. It's going to be an incompressible fluid, of course, it's water. We will allow different constant densities when that is appropriate. The typical density difference is about 0.5 to 1% in the thermocline situation that I showed you for the equatorial flow. So we have got Euler's equation and the equation of mass conservation. Of course, that's not written in a rotating frame, so we might write that in a frame fixed at the centre of the Earth. If we then set up a coordinate system rotating with the Earth, then we'll have to include both the Coriolis and the centripetal terms. We want to introduce a set of right-handed spherical coordinates. So here they are. We have theta is the polar angle, measured north to south. Phi is the azimuthal angle. It's the one that measures around. R is just the radius from the centre of the Earth. The rotation vector, the rotation is about the north-south axis. So we can represent that in this coordinate system. Incorporate all of that into our equations, and we obtain the Euler equation expressed in this particular coordinate system with all the extra terms, nonlinear terms included, that are relevant in this situation, together with the appropriate equation of mass conservation. So, put bluntly, that's what we're looking at. Okay, what about boundary conditions? Well, we're going to have surface boundary conditions, and where there's a thermocline, we're going to have a condition across a thermocline. I'm going to formulate the problem without any mixing, so we've got the conventional kinematic conditions, etc. So, at the surface, we'll have a pressure prescribed, and either in the big scheme of things, I would like to solve the problem where you tell me what the pressure is doing on the surface, we'll see what happens. Generally, of course, that's an immensely complicated problem, but maybe we can formulate some simpler problems, but then we would have to have surface conditions which are consistent with that, which might involve being rather specific about the type of pressure. We also have the kinematic condition on the surface, remember no mixing. Correspondingly, there is a bottom condition, and I'll take the bottom to be a solid, impermeable, and stationary here. If there is a thermocline, then we have a kinematic condition across the thermocline and continuity of pressure across the thermocline. As I mentioned in my preamble, one of the standard simplifications, and it is used a lot, is the tangent plane approximation. I'm not going to derive it, I'm just going to say a little bit about it and write it down for you. So this essentially is based on a tangent plane which approximate what happens locally in the neighbourhood of a point on the surface of the Earth. X follows the curvilinear coordinate that goes in the azimuthal direction. You can either take it on the plane or to this level of approximation it makes no difference. It literally is the curvilinear coordinate, providing you don't go too far. Y likewise is perpendicular to this, sitting in the tangent plane. We introduce a z relative measured relative to an average radius. Oh, it's usual to relabel. I prefer to have the normal sequence of r theta 5 u vw, but if we're going to use x, y, z, which is what they tend to do, then it's more usual to relabel and switch around u and w. What we then write down is values for small z over r, so it's a bit like a shallow water approximation. I'll say more about that shortly, and a very narrow band either side of the particular circle that you are looking at, a great or small circle. I'll just write down the equations as they pertain to the equator to show you what they look like. So that's with that adjustment with the x, y, z coordinates introduced, the conventional Cartesian coordinates introduced. What you'll then see, what I've written down here is what is usually called the beta plane approximation. That includes the next approximation, the linear terms over and above the constant terms associated with the Coriolis. They are the y terms that you can see sitting in the equation. If you remove the y term, so in a sense you're in an even narrower band, then you'll get what is usually called the f-plane approximation. One comment is the nature of the fundamental equations that we're using. We can't prescribe work with the initiator or the driver for this motion. We haven't got any viscous stresses, for example. But what we can do is to construct necessary consistency conditions, if you like, for the existence of solutions of a particular type. Can such a type of solution exist, albeit maybe in an approximate asymptotic sense? Are such solutions available with, we might argue, if you were to put in other physical effects, small adjustments due to the effects of viscous action, friction, something like that. Right, let's get started. So I'm going to quite rapidly work through. I just want to present some ideas to you, present some results without doing any fine calculation. This one in particular is very involved, very messy, but quite routine. In fact, it's the one we started with, and it's the one that I think shows how the techniques of classical elementary, in this case really elementary, fluid mechanics do pay dividends. You can make headway. So I'm going to, because almost all the work that had been done was done using the f-plane approximation, so this is really simplifying the geometry, I'll stick to that. That means essentially we'll have nothing happening in the y direction. We'll have no component in the y direction and no behavior, no variation in the y direction. But we will allow variations in the azimuthal direction. But we won't make any other simplifying assumptions. We'll then just do the best we can with what we have available, bearing in mind we're going to have a linear wave, as I'll describe in a moment, sitting on top of a very complicated flow structure. So we non-dimensionalize in the usual fashion, introduce some appropriate scales, a depth, a speed, and an amplitude. And for what it's worth, that's the non-dimensionalization I'm going to use. We then have to make various choices. The background flow, I want to mirror what I showed you in one of my earlier view graphs. So you can allow slightly more general choices and make headway, but without doubt, the simplest is to use something which involves regions of constant vorticity, as you can see. Importantly, the whole calculation here can be done, and this, in my view, is the strength of using a conventional approach. The whole calculation can be done for arbitrary speed, so you've got the v, which remember is going backwards, if you like, is going from east to west. You've also got the undercurrent, that's down here. You've also got the distribution, the sizes of the regions, all of which involve free parameters. The undisturbed thermocline is sitting at z is equal to -1, which is in this region here. We assume that will always remain, and all the evidence is that it remains in the neighbourhood of the maximum speed of the undercurrent. We can write down the governing equations for the linearized problem, absolutely straightforward. We have a thermocline, so we have a condition on the thermocline. It happens to involve the non-dimensional omega, which I don't think, for reasons when I constructed this, I hadn't non-dimensionalized earlier, but there it is. Right. The development of the solution involves the construction of a solution in 5 regions, so involved, messy, takes time, but absolutely straightforward. All suitable conditions being imposed across the various boundaries, and that includes down here we'll suppose that there is the oncoming flow is essentially stationary. That's typical of the equatorial undercurrent. We have a backwards flow, a forwards flow, a region that then decays and essentially becomes stagnant conditions for the underlying flow field below that. We can solve in this region, this one then below and then above the thermocline, and then in the region in the neighbourhood of the surface. As I said a few seconds ago, this problem can be solved completely. You can write down the complete algebraic structure of this problem, and importantly, for arbitrary wave number. You don't need to restrict it to short or long waves. You can do the calculation for arbitrary wave number. And you can extract a lot of information, as you would imagine. There's a lot of detail there. We obviously get wave speeds, and there are up to 5 waves associated with this problem. There's coupling between the waves and the surface, and we can find out how strong, how weak that coupling is. We can also predict critical layers, and part of the work has been to begin to look at the properties of the critical layers by going back to the original governing equations, looking at those. Critical layers have been observed in this type of flow in the oceans. And I must say that I think we were quite pleased that so much of the basic predictions that we got out of this model did agree pretty well with the data. But before I say any more, let me say that for me, this is the worst type of problem. This isn't really doing what I like doing. I felt it had to be done to show the strength of elementary techniques which go way beyond any of the standard oceanographic results, but it's really not what I'm in the business of doing. Let's see if we can improve things a little. So what we're now going to do is to see whether we can look at that basic type of flow that I showed you in the very first picture. I didn't add, I will now. Not only do you have that flow, well, I guess from west to east, backwards flow, forwards flow. Once you get a little bit off the equator, there are also regions of circulatory flow, upwelling and downwelling, sitting either side of the equator, making it a truly three-dimensional problem. Bear that in mind when I show you pictures in a moment. Because we do want some Y structure now, albeit in a relatively narrow band, because we're using the beta plane approximation. We do use the beta plane approximation. We have some Y structure in the problem. We non-dimensionalize. Now on this occasion, I'm using 3 different length scales for what's happening that way, and that way. There are naturally 3 different length scales associated with this problem. However, a suitable choice, bearing in mind the limited region associated with the beta plane approximation, is to make a choice which essentially measures how far you go away from, in this case, the equator, as you deviate away from the surface by an amount h. There should be a factor 2 in there, but we don't need that for purposes of non-dimensionalization. If you make that choice, that's that choice for L, which is that scale there, then typically the beta plane approximation is deemed to hold, that is the approximations to the trigonometric terms that came through the approximations to the Coriolis, for this Y to be roughly between plus and minus 4. Okay. Having introduced those parameters, made that choice, we then impose just one limiting process only on that full system, equations and boundary conditions, and thermocline. We just ask, what is the leading order approximation if you let h over L tend to 0, all the other parameters, having suitably defined L, fixed? This amounts to having any three-dimensional structure in this plane, well, any two-dimensional structure in this plane, and a slow evolution in the azimuthal direction, in the x direction. Right, this is the system of equations that we then obtain. Observe, of course, we now do have a nonlinear system. In this system, you are able, as we did with the wave problem, we can elect to impose u. We can choose a u, and everything else follows thereafter. Below the thermocline, the p in the equations here would have to be replaced by a small correction factor, p over 1 plus alpha. In what I'm going to show you, because we're looking at the background structure, the presence of a slight change in density doesn't alter the basic velocity field. Yes, it has a very significant effect upon any waves that you might superimpose on the system, but we're not doing that here. This is just the background flow, which, if you like, could be regarded as a precursor to the first problem I showed you. Right, the system that I've just shown you can be solved completely. We can get a complete description via stream functions for that particular, well, a quasi-stream function in that particular case. I'm going to show you a slightly simplified version, one that makes the geometry such that you follow the curvature, if that's the x direction, that covers the curvature as it deviates away from the tangent plane, the quadratic behavior that you get there, that follows that religiously. There are other solutions, though, in which case the problem can be expressed, that's what we had before, can be expressed with the boundary conditions and the behavior of the function u now with the correction factor of a half y squared. You can look for more general solutions. The h of x in here, so this is the free surface, which in this coordinate system I'm now going to take as flat. It is strictly the azimuth, so it's a curvilinear coordinate, but relative to the curvilinear coordinate, there is no deviation. The data that we have available suggests that due to wind action, relative to that curvature line on the surface of the Earth, the western end of the Pacific is about ½ a meter higher than the eastern end. I felt that really was a quite unimportant element within this particular approach to the problem. Small density change can be included, but I'm going to ask that the density change across the thermocline, we can still have a thermocline because it's a line that satisfies kinematic conditions. We can be present. The correction terms due to small density change are easily included if one wants to add that as well. As I've already said, u is then chosen as a function of, let's say, z at a given x and y. Right, so as I've indicated, formulating that problem, which has now got three-dimensionality, the real question becomes what sort of solutions are there? And there are a number of choices available. I'm not going to go through how we make the choices or what the choices are. I will just show you one solution, of which we have many. Here's one solution. Now let me describe this to you. This is a representation of the three-dimensional flow. So this is the equator. This is the chosen superimposed flow field, which therefore is travelling that direction. Either side, I've only drawn one side. Here is a 3-cell structure. We can have 1, 2, and 3 cells. The flow here, by the way, decreasing, slowing down, and becoming 0. Below here, we have 0 conditions. The lines are, at this particular station, indicated by the centre of the imposed flow field. That's this greenish line, and the position of the thermocline, which satisfies a suitable kinematic condition. This then, I may have written it down here actually, I have, and then on top of all of that, there is an evolution in the x direction. Evolution of the position of the maximum speed, which evolves to satisfy the full governing equations, which has got x dependence in it, and also the deviation of the thermocline, which does seem to correspond very well indeed with what is observed. To the extent that a lot of the data on the thermocline for the equatorial undercurrent indicates that it drops slightly as you leave the western end and then gently climbs, and you saw that in the picture I showed you, climbs as you approach the eastern end, and that is recovered precisely in almost all the solutions, no matter what the cell structure happens to be. But that is going into the fine detail of the solution and its interpretation, and I don't really want to do that here. What I wanted to show you was that a standard formulation of a standard problem, albeit in the beta plane, non-dimensionalize, choose the lead, have a look at the leading order. Does that have a solution? Does it have an interesting solution? Does it have a useful solution? Yes, I think, on every count. Okay, while looking at that problem, I noticed that there was an interesting property of the equations that implied that there was probably hidden in that system an exact solution of the original governing equations. And that is what I want to briefly describe to you now. Now, it's a very special solution. Exact solutions generally are not going to describe a particular physical situation. That's not going to happen. But when you have an exact solution, you could then perturb it, use it as the basis for further development by introducing other physical effects, making sure there's a boundary, asking what happens as you go further down with some sort of friction effects, whatever. Maybe by using multiple scales, slow evolution of an exact solution. So bear that in mind. That's typical of exact solutions in fluid mechanics. They are not going to be useful solutions as stand-alone solutions, but they're a very good starting point. Right, so this one is a flow which is purely in the azimuthal direction, so we're going around. There is no flow in the u or the v direction. They're both zero, so it's purely going around. Nothing else whatever is happening. But it can vary in theta, so it can vary like that, and it can vary in r. But there is both u and v zero. Okay, when you impose those conditions, you get this pair of equations. That's what everything reduces to. That system is easily solved. It turns out that w is a function of r sine theta, which is part of associated with the Taylor-Proudman theorem, which I'll mention briefly later on. If we can then determine exactly what the pressure is, we get an expression for the pressure, a bit clumsy, but we can write it down. Then you can either regard this as prescribing the surface and asking what's the pressure got to be to get that surface, or, and solutions do exist the other way around, that is, prescribe the P and determine the H when you evaluate this on R is equal to big R plus H of theta. The same type of exact solution pertains for both the beta plane and the F plane system of equations. The advantage of that is, well, some oceanographers prefer it, but one of the great advantages is that the corresponding relation to this is much, much simpler. It's essentially algebraic, and it's very easy to manipulate and handle and get useful results out of it. So we have an exact solution of that full original system of equations. Having got that solution, the thoughts turned, I think Adrian again prompted me to look at the possibility of using the same sort of idea, but now for the ACC. So that's the one that goes all the way around a polar axis. Does there exist a corresponding solution in that case? Well, we have to make some adjustments now, and it's really rather surprising, I think. When I first did the problem, got nothing like the sort of solutions that could have any meaning in physical reality whatsoever as it pertains to the ACC. It turned out that what you've got to do is to deal with a body force which is non-conservative. Now, let me make a comment. If it's immediately obvious from the equations, it's clearly, of course, therefore obvious from the solution I'm going to show you, that if you, though you may not be able to pick up that detail, if you assume that the body force is conservative, then one of the Taylor-Proudman results comes into play, which says that the speed below the surface is going to be constant on lines parallel to the axis of rotation. So if you're below the equator here, it means that you have constancy in that direction. So if, for example, you have a fast speed for a current on the surface, here's the lower hemisphere, fast speed on the surface, that is propagated all the way through to the bottom. You cannot have any Z, or strictly radial, structure. It's impossible if you have a conservative force field. Indeed, this is well known to the oceanographers. They know that the drivers for many of the flows, and this one in particular, are driven by non-conservative forces. It's very unclear about the details, but we know they are there, and we know the only way to make headway in this sense is to ensure that you invoke non-conservative force system. All right. The structure, though, is otherwise the same as we had before. We just want a purely circulating motion, okay? So U and V are both 0. In fact, it is the formulation that we had before, except that now you have this term in. Okay, you can construct solutions of that system quite straightforwardly for a given G. Of course, we didn't know what G was, but we do have some guidance as to the nature that G might have, but more importantly, we rapidly found out that suitable choices of G can be made, which are physically reasonable and give us meaningful results. Now remember, this is an exact solution for a suitably, carefully chosen G. Okay, so let me try and explain what I've shown there. Again, we have many examples. This is just one to show you what is possible from, this is an exact solution, remember, of the full governing equations. What I've done here is to produce a surface which represents the speed in the flow from the surface downwards, and it's drawn, because we're in Antarctica, I've drawn it in the southern hemisphere. Therefore, let me see if I can get this right. That corresponds to the surface of the ocean. This corresponds to the bottom of the ocean. There we are, that's the bottom of the ocean. We have 0 there, and we can find solutions which are 0 on the bottom and 0 either side. We have a jet. We have a jet that is on the surface, has got this, so it's a maximum speed in the middle, lots of other shapes, just chosen one that's easy to handle. Maximum in the middle, decreases to 0, and that 0 is then maintained through the flow right down to the bottom. What's more, of course, is that you can join a number of these together. If you've got that solution, you can have another one with a 0 in between, and another and another. You can have families of these rotating jet solutions, which, let me emphasize again, are exact solutions of the original governing equations. We have the starting point, but it can only be that, for modeling what happens to flows like the ACC. We could perhaps put slow variations to allow it to wiggle around a little bit, to go around the contours of Antarctica or whatever. That's for the future. Right. I'm going to pause again. Everybody still? Well, you're not saying anything. It just means either you're bored or maybe you're following it all. Large gyres. Again, we're starting from our governing equations allowing vorticity, and it is just a matter. By the way, we just have a conventional body force here. And the driving principle here is solely the shallow water approximation. Can we use the shallow water approximation and nothing more? Where does that lead us in the governing equations? So here we are. We carry out a non-dimensionalisation. The crucial parameter is, of course, going to be the ratio of the scale that we're using to measure, if you like, the depth of the ocean relative to the radius of the Earth. We're not quite sure what the speeds are, but generally what you've got is speeds on the surface are of one order of magnitude, and I haven't separated them out, so both U, V and W have got the same scale. I've just called it capital U. But in the shallow water approximation, the essence of a shallow water approximation is that it's predominantly circular motion and very weak motion in the W direction, in the Z direction, in the conventional Z direction. There are families of solutions of these equations depending on what size you choose for that parameter K. Here we are, that's what I'm just saying. in these motions, and most certainly in gyres, the vertical speeds are something like 10 to the minus 4 times the surface speeds. So it's a factor of 10 to the minus 4 smaller for the vertical speeds within a gyre as opposed to the ones that are driving it round, being driven, but we haven't got the driver here, remember. Right, there's my parameter, there is the shallow water parameter, epsilon is delta over r, and the most natural problem, and again, until you've tried it, you don't really know, the most natural choice from the point of view of the equations and from the type of problem we're interested in is to choose k to be equal to order epsilon squared. I will just in passing say that currently we're looking at a problem to do with Ekman spirals where we definitely need Navier-Stokes, and then it turns out that we can have a lot more structure and solve that problem by choosing that to be epsilon, not as small as it is here. Right, so at leading order, that's the system of equations that we get. I'm not making any other assumptions or approximations here. Non-dimensionalize, bring the parameter in, choose very weak behavior in the w direction, the z direction. What do you get? Well, that's what we get. And of course, as you'd expect, we've got the main structure of the Euler equation there with nonlinearity, of course. There's the pressure condition, and in this philosophy, we're expecting to probably have to choose that to suit the solution that might be of interest rather than be arbitrarily given it, of course. This is just because of the redefinition. There's been a slight adjustment with the way in which pressure is defined in here. Kinematic condition, I think that's it, isn't it? Yeah. Okay. You can make quite a number of different choices, all of which work for the bottom. I'll make the simplest one of all. I just say that d is a constant, so that means it's a spherical surface. Remember, we are in spherical coordinates here. Okay, this system can be solved completely. Introduce a stream function. We then break down the stream function into two parts. There's this part and a more general part. If you put that into the construct the vorticity equation, then we get this. I'm going to pause there for a moment. I want you to look at that before I bring up the next one. Just look at that. Okay. The total vorticity is now made up of this bit and the vorticity that's generated by that term. So we've got two parts to the vorticity. Not surprisingly, there is a vorticity generated due to the fact that the Earth is spinning. Opted to call that spin vorticity, whereas this one is fundamental to whatever is the motion of the oceans. So I'm just going to call that oceanic vorticity. F is an arbitrary function here, and those of you who are familiar with fluid mechanics will know the classical result. That's it, that in this reduction of the geometry, the vorticity is a function only of the stream function. In other words, that term is absent in classical fluid mechanics. But because of the effect of rotation and the transformation needed to get to this stage, what we find is that that function is now shifted by omega cos theta. And immediately there are some rather intriguing questions about the nature of solutions of that equation. And I'm hoping that Adrian will be able to tell me more about that one day. So we can formulate the problem, we can solve it completely. We've got a vorticity equation, but a new type of vorticity equation. But that's almost, it's an intriguing and interesting sideline, but it is really a sideline in terms of the story I'm trying to tell you here. Because what we want to find out is whether, just making that shallow water approximation, do we get any useful solutions out of this system? Right. The simplest one, non-trivial one, is to assume that the oceanic vorticity is constant vorticity. I've called it gamma. We can then construct solutions. For example, there is then, of that reduced system of equations, an exact solution which looks like that. I've deliberately taken the gamma or gamma upon beta out. That just gives you the strength of the flow field, if you like. As you juggle with the two parameters A and beta, you get very many different sorts of solution. I'm going to give you two examples. These are exact solutions of that system, which is in spherical geometry. They are sitting on the spherical surface, and if you adjust these parameters accordingly, then you can have solutions which have a bounding streamline. There is no flow outside, the flow is zero if you like on the outside. There's a bounding streamline and you've got streamlines on the inside. I've drawn two versions here, one in the northern hemisphere and one in the southern hemisphere. Their position and their shape can be adjusted by playing around with the two parameters A and beta. Now I have to tell you there are other solutions of this system. You can get solutions that straddle the equator. Now, we don't have any gyres that straddle the equator, so there are disallowed values of relations between A and beta if you want a physically realistic solution. What's important here is that there are solutions which are highly nonlinear, in spherical geometry, as big as you like. There's no restriction on size here. Those gyres can be as big as you want them to be, and they sit in bounded regions. So they are bounded. The outer ones you can see here are the bounding streamlines. No solution exists outside that particular region. Okay, so in summary, what I've tried to do, rather obviously, is to approach these sort of problems of physical oceanography purely from the Euler equation point of view. I've used the conventional techniques, non-dimensionalized, scaled, and then tried to find some limiting process of the parameters, keeping all the others fixed, which will enable us to extract a useful, interesting, and in an asymptotic sense, a consistent solution. By the way, I should add that it is very, very hard work to check the nature of higher order terms. But it's quite easy to see whether there are any natural singularities that can occur. There are no obvious singularities. As long as you avoid, for example, the equator in some of these problems, or you actually avoid the pole, then there are no singularities appearing in the asymptotic expansions. So it would appear that we've got leading orders which are correct representations, approximately, of the full governing equations. And, well, I hope it's become reasonably evident that once you've done that, that minimizes the approximation. We're not making ad hoc approximations thereafter. We're just taking what we are given and proceeding. So, and we've discussed, well, the simplest problem of all, and particularly a tedious one, but I said at the time I found it had to be done, waves on the EUC. Much more interesting because as far as we can tell, and certainly from all the feedback we've got from the oceanographers, nobody has produced an analytical three-dimensional structure for these sort of flows, which have flow in one direction and upwelling and downwelling and cells or whatever. By the way, obviously, the cells were not closed. Because we're in a neighborhood, we were in the beta plane approximation, the cells look like that. We have no mechanism for closing the cell off. That would be much further away, and we'd have to do a different asymptotic structured solution, which is valid much further away from the equator, as it would be in that case. I've shown you two exact solutions, which, in my terminology, would become building blocks to do far more work later on. That's the starting point. If you can get an exact solution, that's the starting point of a much more detailed analysis, and I'm hoping that we or others who come across this work will be able to take that a little bit further. What I think probably, on balance, is the most exciting here to date, which is still ongoing, is the formulation of a problem that recovers large gyres sitting on the surface of a sphere. And we intend to continue this. It's much ongoing. I made an allusion to the Ekman problem, and it looks as though we've pretty well sorted out a way of tackling and generalizing Ekman flow. And otherwise, it's a matter of putting in slow variations, perhaps taking as background, for example, one that I keep going back to, but I haven't quite managed to find enough time to really work hard at it, is to take the exact ACC flow and then add waves to that and find out the interaction between that and surface waves. That's for the future. Thank you.
Thank you very much. Any questions or comments? Yes, please.
The near equator,
F-plane, beta plane, which one you have to determine which one is better
So which one?
Near the equator?
Near the equator.
You can use the F-plane or beta plane.
Oh no, well beta plane is better because it's got a little bit of y dependence in it. So it's valid strictly a little bit further away. I mean, I think typically...
Even the shallow water?
Oh yes, we're talking about distance away from the equator. It doesn't matter what happens down there. That's okay. Okay? The approximation is this way. Okay? And then it's replaced by a tangent plane. So the beta plane is marginally better than the F plane. But as I've tried to, I hope it's come out, I've tried to move away from that eventually so that we are dealing with the full spherical coordinates and not making any simplifying assumptions about that aspect of the geometry. But beta plane, I think, is typically reckoned to be valid about 2 degrees either side of the, let's say, the equator, whereas the F plane is 1 or 1.5 degrees maybe. After that, when you're larger distances, then you need higher order corrections coming from the trigonometric terms in the Coriolis.
Is turbulence a problem?
Of course it is. Well, I used the word at the very beginning. Of course, what we hope we're describing here is in some sort of very average sense, what you actually see. And that, I can't say any more. Turbulence is a big problem. However, all the evidence would suggest, and I don't just mean this sort of fluid mechanics generally, a large swathe of properties that you see in the average sense are what you can predict from Euler or Navier-Stokes. So that's it. That's the end of it so far as I'm concerned.
Can it move the jet profile, for instance, with respect to turbulence?
I don't know enough about the intricacies of that. I would guess so. Yes, it could. But you need to talk to an expert on ACC, I think. I can't help you. I'm sorry.
I know it's a problem in the coastal regime.
Yes.
But I don't know anything really about the oceanographic regime.
Yes, please.
Yeah, I wonder about the role of the centripetal force or acceleration. Is that just a trivial contribution?
Yes, it is trivial. Essentially adjust the pressure.
Yeah.
That's it. And it's all in the equation. And in fact, a couple of times you'll see that I redefined pressure to be this plus something else, and generally it was taking out the centripetal contribution. Yes, it's generally trivial in these equations. Coriolis, though, is not, because, of course, it links to the velocity field. Yep.
Yes. Other questions? We still have time. May I ask a question about viscosity or turbulent viscosity, anything? In this large scale,
Yes.
is it completely okay to neglect the viscosity?
Oh, no. I mean, I think in many of the things I've described here, there's no evidence that viscosity plays a significant role. However, in something like the Ekman spiral, it's fundamental. And then it looks as though using constant eddy viscosities, and there are 2 of them and they're different, it does seem to work very well indeed, and it seems to be supported by most of the oceanographers as the way forward. But of course, you look at it in fine detail, these eddy viscosities might vary with depth and extent. Not rapidly, but they might vary a little. And there's certainly some oceanographers who think that plays a significant role in some aspects of what we see in the oceans. But for me, that would be a step too far. I'll put viscosity in, I'll put in eddy viscosities, I'll have different viscosities in different directions, but that'd be constant.
I don't know much about this, but it seems to me that for this purpose, we use this viscous model. For this purpose, we use this introduction of new way of viscosity. So I very much sometimes confused. So what kind of viscosity we are?
I suspect it's going to be driven, of course, by the particular sort of problem that you're interested in. And one might be intrinsic, one sort of viscosity might be intrinsic to one, whereas something different might be intrinsic to the other. It's a bit like saying we'll work with the Euler equations or we'll work with Navier-Stokes. We know that is not absolutely perfect, but I reckon they're a darn good starting point to understanding what's going in the fluid flows that we see around us. But not the end, only the start.
Questions? Yes, please.
A symptomatic question, say in general, if people use, say, beta plane, does it represent the main term of some valid asymptotic procedure, or this is purely physical still?
That's a good question, and I have to say I don't treat it as a proper asymptotic procedure. To do that, I would have to argue that there's a scale associated with the y, and we're letting y tend to 0. As y increases, it becomes non-uniform, and you have to do matching or whatever else to it. So I regard it as just an ad hoc approximation. But it does mean that if you're going to apply it, as the oceanographers do, and it is certainly useful in some respects, it has to be used in a very limited sense indeed. I think that's the best answer I can give you, I think.
Okay, then let us thank the speaker again. And we have a coffee break, and please come back here at 11:30.